Hi everyone, I'm Mr. Fullerton, and today's topic is energy level diagrams. Objective for today will be calculating the energy of an absorbed or emitted photon from an energy level diagram. So energy level diagrams are tools that we use to visualize the allowed electron energy levels in an atom. The lowest energy level is known as the ground state. Let's take a look at an energy level diagram for hydrogen. We can see over here on the left that we have negative energies in electron volts that indicate the electron is bound to the atom. So it's almost as if the electron, while it's in these levels, is stuck to the atom. You have to get up here to zero, out of the negatives, in order for the electron to be free, to become a photoelectron, to be emitted. As long as it has a negative energy, it owes energy to the atom. It's stuck there. It can't leave. On the left-hand side, you can see our lowest energy level, n equals 1, is listed as the ground state, and that's at negative 13.6 electron volts. To get to the n equals 2 state at negative 3.4 electron volts, it would have to absorb a photon of energy 10.2 eV. And so on. To get to the next level, it would have to absorb enough to get to negative 1.5 eV, and so on. If an electron is in the ground state of a hydrogen atom, in order to be ionized, to become free, if it starts at negative 13.6 electron volts, it would have to absorb a photon of at least 13.6 electron volts in order to be free. Any energy above and beyond that becomes the kinetic energy of the electron. So let's see how we can use this in a sample problem. An electron in a hydrogen atom drops from the n equals 3 state, right here, to the n equals 2 state. Determine the energy of the photon, the emitted radiation that is given off. Well, the energy of a photon that's emitted is equal to the initial electron energy level minus the final electron energy level. The initial energy level, here at the n equals 3 state, is negative 1.51 eV, minus the final energy level is negative 3.4 eV. So negative 1.5 eV minus negative 3.4 eV gives us an energy of the photon of 1.89 eV. So the photon that's emitted will have an energy of 1.89 electron volts. Let's look at another one. What is the frequency of a photon emitted when an electron in a hydrogen atom drops from the n equals 2 to the n equals 1 energy level? So here from 2 all the way down here to n equals 1. Well, we'll first start by finding the energy of that photon again. Energy of the emitted photon is equal to the initial electron energy level minus the final electron energy level, or negative 3.4 eV minus negative 13.6 eV, which is 10.2 electron volts. So the emitted photon's energy is 10.2 eV. Now if we want to figure out the frequency, we can use our formula, E equals HF, but remember our energy has to be in standard SI units. So we need to convert 10.2 eV to joules first. So that's 10.2 electron volts. We want electron volts to go away. We want to convert to joules, and I know 1 eV is 1.6 times 10 to the minus 19 joules. My electron volts make a ratio of 1, and I end up with an energy of about 1.63 times 10 to the minus 18 joules. Now I can solve for the frequency of the emitted photon. E equals HF, which implies then that the frequency is going to be the energy over Planck's constant H, or 1.63 times 10 to the minus 18 joules over 6.63 times 10 to the minus 34 joule seconds, which gives me a frequency of right around 2.46 times 10 to the 15 hertz. All right. Now you can look up energy level diagrams for more than just hydrogen. For example, here's an energy level diagram for Mercury. Notice that we have different values for the different energies, And in the case of Mercury, the levels are named by letters. Instead of the n equals 1, n equals 2, n equals 3 state, we have the A, B, C, D, E levels, and so on. So let's see how we can use this to solve a couple problems. If an electron in a mercury atom drops from energy level F to energy level C, what is the energy of the emitted photon? Well, again, the energy of a photon must be the initial electron energy level minus the final electron energy level. Or in this case, that'll be negative 2.68 eV minus negative 5.52 eV, which gives me an emitted photon energy of 2.84 electron volts. All right, let's look at one more. A mercury atom in the ground state absorbs 20 electron volts of energy and is ionized by losing an electron. How much kinetic energy does this electron have after the ionization? So in this case, we have an electron absorbing energy and being emitted as a photoelectron. Well, in order to solve this, we have to realize that our electron is going to start here at the ground state. It's going to absorb 20 electron volts of energy. That's going to take it up to this ionization state, and then any extra energy is the kinetic energy of our emitted photoelectron. So if we start with 20 electron volts, we use up 10.38 going from the ground state to ionization. So that's going to leave us with 9.62 electron volts. That extra 9.62 electron volts must be the kinetic energy of the emitted photoelectron. Hopefully this gets you started with energy level diagrams. If you need more help or are looking for more information, check out aplusphysics.com. Thanks and make it a great day.